Hello, everyone. Welcome to the Pure AI podcast, where actual human journalists dig deep into the world of artificial intelligence, and then AI shows up for the audio conversion. I'm John K. Waters, editor in chief in the Converge 360 group of 1105 Media. And joining me now, as always, is a woman who once edited an 80-page AI white paper using nothing but sarcasm and a post-it note. Our illustrious editorial director, Gladys Rama. Hi, Gladys. How goes the war with the machines?
Hey John, let's just say AI is no longer knocking at the door. It's letting itself in, reorganizing your files, and suggesting a more efficient way to write your job description. And maybe doing it better than you. So, what's on deck today?
Today, we're talking about a report from our in-house analysts published this week in Pure AI, Understanding AI Large Language Model Transformers, an analogy for mere mortals.
I love this report. That's the thing about these complex AI systems, right? They seem like magic until you find the right analogy to understand them. And I think we've got a really good one today.
Me too. The report basically turns this transformer technology into something that feels familiar, like, like a factory with different departments and workers, all doing their part to create something amazing. I think it's going to change the way our readers think about these AI systems.
Okay, so when I first started reading about these large language models like GPT, I have to admit I was a bit overwhelmed.
The thing about these LLMs is that they're massive, you know? We're talking about systems with hundreds of billions of parameters that are that are processing information in ways that even many engineers struggle to fully grasp.
What I did understand is that there's this key component called a transformer that's at the heart of all this.
Exactly right. The transformer is really the essential architecture that powers all modern LLMs. It's it's what allows these systems to understand context and generate coherent responses. But here's the thing. Explaining how transformers actually work is incredibly challenging.
Why is that so difficult to explain? Besides the obvious technical complexity.
Well, see, most explanations out there fall into one of two categories. They're either way too technical with all the math and jargon that only AI researchers understand, or they're so simplified that you don't actually learn anything useful about how they function.
So we need something in the middle, something that actually helps people understand without requiring a PhD.
Precisely. And that's why I love this factory analogy. It's actually based on internal training material from a major tech company that uses this to help their employees get their heads around AI concepts.
So instead of getting lost in like technical details about attention mechanisms and neural networks, we can think about it as a factory with workers doing different jobs.
Exactly right. And that this approach actually helps people with all kinds of backgrounds, from business professionals to curious enthusiasts, to understand what's happening behind the scenes when you interact with ChatGPT or similar systems. It gives you a mental model that's close enough to be useful.
Okay, so give us the big picture. How does a factory represent a language model?
So imagine that a large language model as a factory, right? Let's call it the Acme Company factory. And this factory has one main job. It takes in raw materials through the loading dock, processes them through various departments, and then ships out a finished product to customers.
And what exactly are these raw materials in our analogy?
The raw materials are essentially, they're just sequences of words, you know? Like when you ask a question such as, how can I make an apple pie? That's your raw material going into the factory. And then the finished product is the detailed instructions for making the apple pie that comes out the other end.
That makes sense. So different parts of the factory handle different aspects of processing that text.
Exactly. Just like a real factory has different departments, like, payroll to handle salaries, security to keep everything safe, human resources doing, well, whatever HR actually does, right? And accounting to track resources. But the most important department in our factory analogy is manufacturing. That's where all the actual work happens. And that's what represents our transformer module in the LLM.
So what kind of workers do we have in this manufacturing department?
Great question. So in our manufacturing department, we have eight eight different job positions. We've got the loading dock workers, material sorters, high level supervisors, low level supervisors, analysts, expediters, ordinary assemblers, and finally the final assemblers. Each of these positions represents a specific function in how a transformer processes language.
That's a lot of different roles. Do they all work together in sequence?
Yes and no. They do work in a kind of sequence, but some processes happen in parallel. And and there's actually a lot of back and forth communication between different groups. It's really more like a coordinated dance than a simple assembly line, if that makes sense. The beauty of this analogy is that it helps us visualize how all these components interact without getting lost in the technical weeds.
I can already tell this is going to be helpful. So, what does the first group do?
So the loading dock folks, they're the first point of contact. They take those raw words coming in and convert each one into a set of numbers, what AI folks call vectors. This process is called word embedding, and it's super important because machines don't understand words. They only understand numbers, right? So that's where our journey through the factory begins.
So these loading dock workers, they're essentially translating our human language into something the machine can understand.
Exactly, exactly. Think of it like this. When you and I hear the word apple, we immediately picture, the red fruit, or maybe an iPhone. But the machine has no concept of what an apple is until we convert it into numbers. So the loading dock employees, they take each word and transform it into a unique set of numbers, a vector that represents that word's meaning, its its relationships to other words, and all its possible contexts.
That's fascinating. How does that actually work in practice?
Each word gets represented by maybe hundreds of numbers that capture different aspects of its meaning. The word bank might have numbers that connect it to money, financial institutions, but also to riverbanks, right? The system learns these representations during training by seeing words used in billions of different contexts.
Okay, I think I get the word embedding part, but what about these material sorters you mentioned?
Right, so after the loading dock converts words to numbers, we have the material sorters. These folks are handling what's called positional encoding, and it's really, really crucial because, word order matters tremendously in language.
Can you give me an example of why that would be important?
Yeah, think about these two sentences. The dog bit the man versus the man bit the dog. Same exact words, but totally different meanings because of the order, right? The material sorters are basically adding another set of numbers to each word vector that says, I'm the first word, or I'm the fifth word. Without this, without this information, the model would lose track of word order, which would be a complete disaster.
So these positional encoders, they're basically adding timestamps or sequence numbers to each word.
That's a great way to put it. They're adding sequence information so that the factory knows the difference between how do I bake a pie and a pie I do how bake. Even though they contain the same words, only one makes sense because of the order.
Do these positional encodings just count up in order like one, two, three, four, or is it more complex than that?
It's actually more sophisticated than simple counting. The encodings use sine and cosine functions to create patterns that help the model understand both absolute position, like I'm the third word, and relative positions, like I'm two words away from another word. This helps the model maintain understanding of relationships between words that are close together and words that are far apart in a sentence.
So at this point in our factory, we have words converted to numbers and we know their positions. What happens next with all these encoded materials?
Well, now we've got our raw materials processed into a format the factory can work with, and we're ready for the supervisors to step in. These supervisors are going to start looking at relationships between the words, which is where things get really interesting, and honestly, where the real magic of these systems starts to happen.
So now we've got our words transformed into numbers with their positions marked. What exactly do these high level supervisors do in our factory?
So these high-level supervisors, they're handling what we call multi-headed attention, and it's honestly one of the coolest parts of the whole system. Basically, um they're overseeing both the input and output streams, right? and they're figuring out which parts of the text should be paying attention to other parts.
What do you mean by paying attention to other parts?
Think about it like this. When you're reading a sentence, some words naturally relate to other words, right? Like if I say the cat chased its tail because it was bored, you automatically understand that the first it refers to the cat, and the second it also refers to the cat, not the tail. The high level supervisors are assigning like numeric values to show how strongly words are related to each other.
So they're creating some kind of relationship map between different words?
Exactly. And the multi headed part means they're doing this relationship mapping from multiple perspectives simultaneously. Like one head might focus on grammatical relationships, another on semantic similarities, another on contextual clues. It's like having several different people analyze the same conversation, but each paying attention to different aspects.
So it's not just looking at word relationships from one angle.
Right, right. And that's super important because language is incredibly nuanced. The word bank needs different types of attention if we're talking about money versus if we're talking about a river, you know? Multiple attention heads help capture all those different dimensions of meaning.
That makes sense. What about the low level supervisors? How are they different?
So the low level supervisors are handling what's called self attention, while the high level folks are looking at the big picture. These guys are zooming in on individual input streams. They're really looking at how each word relates to every other word in that specific input. Let me give you an example.
Can you give me an example of how that would work?
Sure, let's say our factory gets the input. If I wanted to bake a cherry pie, how would I do it? The self attention mechanism will assign higher relationship values between it and bake and between it and pie than it will between it and cherry. Because contextually, the it is referring to the action of baking a pie, not to the cherry itself. You know what I mean?
I get it. It's figuring out which words are actually related in meaning, not just which ones are close together.
Exactly. And this is critical for understanding language because meaning often depends on relationships between words that might be separated by several other words, like pronouns referring back to nouns mentioned earlier, or verbs relating to subjects, or or adjectives describing specific nouns.
How does the model actually calculate these relationships?
Well, without getting too technical, each word is essentially asking every other word, how relevant are you to me? And those relevance scores get converted into weights. The higher the weight, the more influence that word has. Then the system combines all this weighted information to create a new context aware representation of each word. It's like it's like each word is updated with awareness of all the other words that matter to it.
So, between these high and low level supervisors, the model is building a comprehensive understanding of how each word relates to every other word.
And that this attention mechanism is what allows these models to handle long range dependencies in text, like understanding that the subject from the beginning of a paragraph is still relevant at the end. You know, it's one of the key innovations that makes these large language models so much more powerful than previous approaches.
So, we've talked about these supervisors who figure out the relationships between words. What happens next in our factory analogy? Who takes all that information and does something with it?
Right. So next up we have what we call the analysts, and they're basically the workhorses of the whole operation. These analysts represent the neural networks in our transformer model, and they're doing like incredibly complex calculations behind the scenes.
What kind of calculations are we talking about?
Well, they're taking all this processed information from the material sorters and both levels of supervisors, right? And they're combining everything using these neural networks to generate this preliminary set of instructions. It's still in numeric form at this point, not words yet, but it's getting closer to our final output.
So, neural networks, what are they actually doing in this context?
Think of neural networks as these incredibly powerful pattern recognition machines. They're they're basically taking all those relationships and patterns that the supervisors identified and running them through this complex web of mathematical operations. It's like, you know, millions of little decisions being made all at once about how to combine and transform the information.
That sounds incredibly complicated.
Oh, it absolutely is. That's why we need these analogies in the first place. The math involved is just, it's mind boggling, really. But what's happening at a high level is that the neural network is learning which patterns in the input are most important for generating a good response.
So, how does it know which patterns are important?
That's where the training comes in. Before the model ever answers a single question, it's trained on just massive amounts of text. During that process, it's essentially learning, if I see this pattern of words and relationships, then this other pattern is likely to follow.
I see. So, in our factory analogy, the analysts have learned from experience which manufacturing steps to take when they see certain types of materials come in.
Exactly. They've seen so many examples that they've developed this intuition, right? Like, oh, when someone asks about making an apple pie, here are the typical steps that follow. And the neural network part is what allows them to combine and process all this information in really sophisticated ways.
What makes neural networks so special compared to other types of calculations?
The magic of neural networks is their ability to handle nonlinear relationships. Like traditional computing is good at if A then B type logic, but language doesn't work that way. Language has all these subtle, complex relationships that aren't straightforward. Neural networks can capture those complicated patterns because they're essentially these massively parallel processing systems with multiple layers of computation.
So, in our factory, the analysts are taking all the tagged and relationship mapped materials and figuring out what to do with them.
Yeah, and not just what to do with them, but how to transform them into something new. They're taking the input, like how do I make an apple pie, and using all this complex pattern matching to start generating the instructions for actually making the pie. But it's important to remember that at this stage, it's still just a preliminary output. It's going to go through more refinement before it becomes our final answer.
And everything is still in number form at this point, right?
Absolutely. The whole factory is processing numbers, vectors, mathematical representations. The words only come back at the very end. That's what makes this whole process so powerful. By turning language into math, we can apply all these incredible mathematical tools to understand and generate text. It's like it's like the model is thinking in this universal mathematical language that can capture the nuances of human communication.
So, after all these complex calculations by the analysts, what happens next in our factory process?
Well, next we have what we call the expediters, and they're doing something really important that's often overlooked in these systems. They're basically monitoring everything that comes out of the analyst's work.
What exactly are they monitoring for?
So the expediters in our factory analogy, they represent what we call residual connections in transformer models. They're constantly checking the outputs produced by the analysts against the original numeric inputs that came into the system. It's like it's like a quality assurance step, you know?
Oh, so they're making sure nothing important gets lost along the way?
Exactly. Because, see, as information passes through all these complex transformations, there's always a risk that some of the original signal could get, like, distorted or even completely lost. The expediters are basically creating these shortcuts or direct connections between earlier and later stages of processing.
That's interesting. Why is that necessary?
It's necessary because without these residual connections, these really deep neural networks would actually struggle to learn effectively. Like, imagine if you were playing a game of telephone with 12 people. By the time the message reaches the end, it might be completely different from what you started with, right?
Right, I see what you mean.
Yeah, and these residual connections, they're like they're like allowing someone at position 6 to hear what was originally said at position 1 and then combine that with what they heard from position 5. It helps preserve the original information throughout the whole process.
So, what else do these expediters do in our factory?
They also perform what we call layer normalization, which is kind of like quality control to guarantee consistency. So not only are they checking against the original input, they're also making sure that the signals being passed forward are well balanced and standardized.
What do you mean by well balanced and standardized?
Well, think about it this way. In a real factory, you might have materials that are wildly different sizes or quantities, right? And that would make assembly really difficult. Layer normalization is like making sure all the components are properly sized and proportioned before they move on to the next stage.
Oh, I get it. So it's keeping everything in the right scale so the next processes can work effectively?
Yes, exactly that. And it's really crucial for the stability of the whole system. Without this normalization, some signals might become too dominant while others get completely ignored, and that would lead to like really poor quality outputs.
This all sounds incredibly thoughtful and well designed. I'm amazed at how many quality checks are built into the process.
Yeah, and that's actually one of the brilliant things about transformer architecture. It has all these mechanisms built in to prevent information loss and maintain signal quality throughout this incredibly complex process. The expediters might not be doing the flashy work of the analysts, but without them, the whole factory would probably fall apart.
So, after the expediters do their work, where does all this processed information go next?
Well, that's when we get to the assembly line process, where teams of assemblers start putting everything together. The assembly line is where all this complex information finally starts to come together.
So, who handles this assembly process in our factory analogy?
At this point, all that processed information is sent to what we call the ordinary assemblers. These assemblers, they take everything that's been processed so far, all the embedded words, the positional data, the attention mechanisms, the neural network outputs, the quality checks, and they combine it all to produce an output.
But that's not the final output yet, right?
No, no, not at all. See, and this is where it gets really interesting. That output is then sent to another team of assemblers who like repeat the whole process to refine it further. And then that refined output goes to yet another set of assemblers, and so on and so on.
Almost like an assembly line with multiple stations?
That's exactly what it's like. Each set of these assemblers represents what we call a transformer layer in the actual AI model. And these layers, they're stacked one after another, with each one taking the output from the previous layer and processing it further.
How many of these assembler teams are there typically?
It really varies depending on the model, but six is kind of like the normal default in many systems. But some of the really big models have way, way more. GPT-3, for example, has 96 layers, which would be like having 96 teams of assemblers, each refining the work of the previous team.
Wow, that's a lot of processing. But why do we need so many layers? Couldn't we just do all the work in one big step?
That's a really good question. The thing is, each layer can only make incremental refinements to the output. It's like polishing a gemstone, right? You start with rough sandpaper and gradually work your way to finer and finer grits. You can't just jump from rough stone to perfectly polished in one go.
That makes sense. And I'm guessing each layer might focus on different aspects of understanding the text.
Yes, that's absolutely right. Research has shown that early layers tend to capture more basic linguistic features like syntax and grammar, while deeper layers get into semantics, meaning, and even abstract reasoning. It's like it's like the early assemblers are putting together the basic structure, and then each subsequent team adds more and more sophisticated details.
So, after all these teams of ordinary assemblers have done their work, what happens then?
Then we finally reach the final assemblers, who have a pretty straightforward but vital job. They take all this numeric output, because remember, everything inside the model is still in number form at this point, and they convert it back into text that humans can actually understand.
Right, because we started with text, converted it to numbers for processing, and now need to turn it back into text.
Exactly. The final assemblers essentially reverse the embedding process that happened at the loading dock. They translate all those number vectors back into words and sentences that make sense to us, and then they emit the final output, like our apple pie recipe or whatever was requested.
This whole process is just incredible when you think about it. Each piece builds on the previous one in such a clever way.
Yeah, and all of this happens in just a fraction of a second. Like all these assemblers, all these layers processing and refining the information, it's all happening almost instantaneously when you ask a question to ChatGPT or any other LLM.
It's like having an entire factory that can produce a completely custom product in seconds.
And the cool thing is, this layered assembly approach is what gives these models their power to generate such nuanced, context aware responses. Each layer adds another level of refinement, another level of understanding to the output.
So, let me take a step back for a moment. This factory analogy we've been discussing, do you think it actually helps people understand what's going on inside these complex language models?
Oh, absolutely. I think it really, really does. See, the whole point of an analogy like this is to take something super technical and abstract and, make it relatable. Most people have some concept of how a factory works, right? So linking these complex AI processes to something familiar, it's like building a bridge between the known and the unknown.
I can see that, but who benefits most from this kind of explanation?
It works for so many different audiences, like business professionals who need to understand AI capabilities without getting lost in the mathematical weeds, or policymakers who are trying to regulate these technologies, or even, just curious people who want to understand the tech that's increasingly part of their daily lives.
I've noticed that most explanations of transformers tend to go in one of two directions, either way too technical or way too simplistic.
That's exactly the problem. On one end, you've got these super detailed academic papers with like pages and pages of matrix multiplication formulas that only specialists can understand. And then on the other end, you've got these oversimplified explanations that basically just say it's magic and don't really tell you anything useful. I think this analogy hits a sweet spot in the middle. It doesn't get bogged down in the mathematical details, but it still gives you a genuine understanding of the architecture and how the different components work together. It's like it's like knowing how a car works without needing to design the engine yourself.
But let's be honest about the limitations here. Every analogy breaks down at some point, right?
I do think it's important to acknowledge its limitations. In real transformer models, there's no actual loading dock or supervisors. These are just conceptual frameworks to help us understand what's happening with the data. The real processes are mathematical operations performed on tensors and vectors in high dimensional spaces.
What would you say are the biggest simplifications in our factory analogy?
Hmm, Probably the biggest one is that we're describing everything as a linear process, when in reality, many of these operations happen in parallel. And we're also not diving into how the model actually learns during training, that whole process of adjusting billions of parameters to improve its output.
Right, we're mostly describing how an already trained model processes information.
Exactly. And there's also the fact that real transformers have additional components and optimizations that we didn't cover. But that's the trade off, right? If we included every detail, we'd be right back to the impenetrable technical explanations we were trying to avoid.
Do you think understanding the basics of how these models work actually helps people use them better?
I really do, yeah. When you understand that an LLM isn't actually thinking, but instead making statistical predictions based on patterns it's seen, it helps you interpret its outputs more critically. You start to see where it might go wrong or have limitations. And that's very valuable whether you're developing with these models or just using them. So, how do you think understanding all of this factory model and how transformers actually work, how does that translate to practical benefits for our listeners, like in their everyday interactions with AI? The thing is, when you understand even just the basics of how these models work, it completely transforms how you interact with them. Like it's not just academic knowledge, you know, it's actually super practical. Understanding that these models work with patterns rather than like true comprehension helps you craft better prompts. When you realize that the loading dock is embedding your words into vectors and the supervisors are figuring out relationships between them. You start to see why being clear and specific in your instructions really matters.
That makes so much sense. I've definitely noticed that sometimes when I ask an AI something vague, I get these rambling, unfocused answers.
Exactly. And that's because, see, the model doesn't really understand your question in the human sense. It's making statistical predictions based on patterns. So when you give it a vague prompt, it has too many possible directions it could go.
What about debugging problems? Like when AI gives you weird or wrong answers?
That's another huge benefit. When you understand the factory process, you can start to diagnose where things might be going wrong. Like maybe there was an issue with self-attention where the model didn't correctly connect references in your text. Or maybe the analysts in our factory analogy made connections that humans wouldn't make because the model was trained on different data than your context.
I never thought about it that way, that knowing the structure helps you troubleshoot.
And beyond just practical usage, it gives you a more realistic view of AI capabilities and limitations. You're not surprised when it makes certain kinds of mistakes, and you know what tasks it's more likely to excel at.
What kinds of tasks would those be based on this transformer architecture?
Well, these models are really, really good at tasks that involve recognizing and continuing patterns, right? So, summarization, text completion, creative writing, all those leverage the strengths of how the assemblers in our factory work together to build coherent outputs. But they might struggle with, tasks requiring factual accuracy or logical reasoning, since they're ultimately pattern matching, not reasoning tools.
That's such a helpful perspective shift, understanding what's actually happening under the hood.
Yeah, and it also helps you be more conscious about ethical issues. When you realize these models are essentially sophisticated text prediction engines built on existing data, you understand why issues like bias can emerge and why careful prompt engineering and output verification are so important in sensitive applications.
So, the takeaway is that this factory analogy isn't just about satisfying curiosity, it's actually empowering users.
Exactly. Knowledge is power, right? The more you understand about how your tools work, the more effectively you can use them, and the better you can communicate their capabilities and limitations to others.
So, we've covered a lot of ground today, haven't we? From loading docks to final assemblers, we've really unpacked this whole factory analogy for understanding transformers.
We have. This analogy takes something incredibly complex and makes it, digestible for anyone, regardless of their technical background. That's what I love about it.
What would you say are the key points you hope our listeners take away from today's episode?
So, the main thing I want everyone to remember is that these AI systems aren't magic. They're processes, right? They're like factories with different departments all working together. Understanding that basic structure helps you work with AI tools more effectively and have more realistic expectations about what they can and can't do.
I really liked how the analogy breaks down each component too. From word embedding at the loading dock to those teams of assemblers refining the output.
Exactly. And remember, these models don't actually understand anything in the human sense. They're just incredibly sophisticated pattern matching systems. That's that's the critical insight that changes how you interact with them.
Well, I've certainly learned a ton today. Thanks so much for walking us through all this, John.
It was my pleasure. I just love talking about this stuff. And I hope our listeners found it useful too.
Before we wrap up, I wanted to remind everyone about the upcoming Visual Studio Live conference happening this August at Microsoft headquarters in Redmond, Washington.
The belly of the beast.
From August 4th to 8th, join fellow developers, Microsoft engineers, and industry experts for 5 days of deep dive, hands-on training. Whether you're building with .NET 8.9, Blazor, Azure, or tapping into the power of GitHub Copilot, ChatGPT, and the semantic kernel, this event puts you at the epicenter of modern app development.
This is one of my favorite events. You'll find practical sessions on everything from AI-enhanced DevOps and cross-platform development with .NET MAUI to cloud architecture and agentic AI workflows, all designed for working developers, not just enthusiasts.
It's more than just learning. It's a chance to connect, get inspired, and walk away with real tools to apply immediately on the job. Head to VSLive.com to view the full agenda and register.
And that's it for this episode of the Pure AI Podcast. Thanks, everyone, and have a great day.